Good morning, good afternoon, good evening, whichever time you're watching this video. I'm Diki Sherpa of third semester in Government College, and my roll number is 21NS0227, and I'm presenting my PPT or a report on topic Bose-Einstein condensation. Let's begin. Contains, these are my contain, and then moving to the next slide. What is Bose? Before understanding Bose condensation, let us understand what is Bose condensate. A Bose condensate is a state of matter that is typically formed when a gas of boson at very low density is cooled to a temperature very close to absolute zero, minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. And what is Bose condensate is? It's typically a state of matter. What does a Bose condensate look like? This is a drop of condensate at the center. The condensate is surrounded by uncondensed gas atom. Let's look how does it look in the next slide. It's look like this. Moving to the next slide. Discovery of Bose-Einstein condensation were first predicted theoretically by Satyendranath Bose, an Indian physicist who also discovered the subatom particle name for him, the Bose. Moving to the introduction, as a gas of bosonic atoms is cooled very close to the absolute zero temperature, their characteristics will change dramatically. More accurately, when its temperature below a critical temperature Tc, a large fraction of the atom condensates in lower quantum states. This dramatic phenomenon is known as Bose-Einstein condensation. Bose and Einstein. In 1924, an Indian physicist named Bose derived the Planck's law of black body radiation by treating the photon as a gas of identical particles. Einstein generalized Bose's theory to an ideal gas of identical atoms or molecules for which the number of particles is conserved. The equations which were derived by Einstein didn't predict the behavior of atoms to be any different from the previous. Einstein found that when the temperature is high, they behave like ordinary gases. However, at low temperature, Einstein theory predicted that a significant proportion of the atoms in the gas will collapse into their lower energy level. This Bose-Einstein condensation. Basically, a Bose-Einstein condensation is a state of a matter where we no longer possible to distinguish between the atom. Criterion for Bose-Einstein condensation at high temperature or weakly interacting gas can be treated as a symbol of Bilbard pulse. In a simplified quantum description, the atom can be regarded as a red packet with an extension del x, approximately given by Heisenberg uncertainty relation. Del x is equal to h by del p, where del p denotes the width of the thermal momentum distribution, when del x is the approximately equal to the thermal de Broglie wavelength del lambda dB, where the matter wavelength for an atom moving with the thermal velocity. When the gas is cooled down, the de Broglie wavelength increases. At the BC transition temperature, lambda dB becomes comparable to the distance between atom and the Bose condensate form, which is characterized by a microscopic population of the grounded state. of the system. As the temperature approaches absolute zero, the thermal cloud disappears, leaving off blue, pure Bose condensate. Here the figure is given. Moving to the next slide. Phase diagram. The green line in a phase boundary. The exact location of the green line can be moved around a little bit, but it will be present. It will be present for just about any substances. Underneath the green line, there is a huge area that we cannot get to. In the condition of the thermal equilibrium is called a forbidden region. As you can see in the figure, this is the forbidden area. Moving to the next slide. Fermions and the Bose. Not all particles can have BEC, Bose-Einstein condensation. This is a relation that the spin of the particles, single protons, neutrons and electrons, have a spin of half. They cannot appear in the same quantum state. BEC cannot take place. Atoms contain an even number of formations. They have total spin of a whole number. They are called boson. Example A, 23NS atom have 11 proton, 12 neutron and 11 electron. As you can see in the figure, fermions have opposite spin, whereas bosons have same spin. The strange state of BEC, when all the atoms stay in the condensate, all the atoms are absolutely identical. There is no possible measurement that can tell them apart. Before condensation, the atoms look like fuzzy balls. After condensation, the atoms lie exactly on the top of each other as a super. Interference pattern. When two Bose-Einstein condensates separate out, their interference pattern reveals their wave nature, as you can see in the figure. Application and further scope. This is in a completely new area. Application are too early to predict. The atom's laser can be used in atom opticals, studying the optical properties of atom lithography, fabricating extremely small circuits, precision atom clocks, order measurement of fundamental standard hologram, communication and computation, fundamental understanding of the quantum mechanics model of black holes. Molecular BEC form fermions. This is the evidence for condensation of pair of allied atoms on the PCS sides of the phase batch. Resonance. The condensate frictions were exact form image like this, using a Gaussian fit friction for the thermal part. Molecular BEC form fermions. As you can see in the figure. Moving to the next slide. Vortices. Vortices. When the condensate is rotated, vortices appear. Vortices. When the condensate is rotated, vortices appear. As you can see in the given figure. Moving to the next slide. Conclusion. The Bose-Einstein condensate can be only achieved when you cool gases down to a non-Kelvin temperature. You have to go very close, absolutely safe. Thank you.